Hello, welcome to our channel again. So I'm Suraj with a new video of mine, and today we are going to discuss another topic in the quantum mechanics, which is the spin states in the quantum mechanics. Or generally, we are going to define the mathematical formulations of a spin, on which axis what is the probability of getting the particular value of a spin. So in the spin there contains two lectures. So in the first part we'll discuss about the spin, the commutation relationship between a spin and some of its mathematical formulations, and in the next video we are going to discuss a detailed mathematical concept in the spin. So let's start our today's video. So first of all, what exactly is the spin? So a spin can be also thought as the angular momentum of the particle which is spinning upon its axis. But you know that a spin has really a deep meaning in context in the quantum mechanics. Spin is the inherent property. Spin is the inherent property of the particular particle. And you know, it is not like the spinning ball, like there is a ball and this is a spinning like this on its this particular axis with some omega, but you know that spin is just different in the context of quantum mechanics. So for simplicity, we only imagine that yes, particles are like this and that is spinning on the three axes. Maybe the axis is a y-axis which is spinning. Regarding the z-axis, it is spinning, and the y-axis. There are three defined axes for our measurement of the spin of the particle. But you notice the spin has really a deep meaning, and a spin requires another great detailed video of actually understanding that what exactly the spin is. So now we are started going to discuss some of the various things about the spin. So first thing about the spin is that spin can be sx, as you know that in sx direction, in as y direction we can measure the spin, and respectively in the sz direction we can measure the spin. But you know that spin also has the commutation relationship. So first of all, in the spin is it also follows the commutation relationship, like the position and the momentum. It also follows the commutation relation. Like for example, let me recap you regarding the example of the position and the momentum. You can see that the position and the momentum operator commutation relationship is equals to the iota h cut. And you know that if any of the two operators are there, which is let's say q operator and let's say j operator are there, and if their commutation relationship is not equals to the zero, as in the case of their position and the momentum, these two particles cannot be measured simultaneously. These two things cannot be measured simultaneously, and this is a property what we are going to study in the spin. So in the spin context, there's also relationship between this, like you can't measure the spin on the two axes simultaneously, and there is also a commutation relationship which follows this. So this is our first commutation relationship, and let me write this second. So this is our first relationship. The second is also similar like this, which is sy and sz is equals to the iota h cut sx. This is our second, and our third is between the sx and the sz, and it is equals to the iota h cut sy. So you know these three are the commutation relationship between the measuring the spin of the particle in the defined axes. Just like the position and momentum, you can't measure the spin of the particle in x and y direction simultaneously. There is always an uncertainty in the measurement, not the precise calculations on the basis of the sx and sy. Okay, so this is the thing that it also follows the commutation relationship, and this is also very important. And you know that the numericals from this particular topic is also very high. But what is the proof of this? That the sx and sy is equals to the iota h cut sz and simultaneously. What is the proof of this particular expression? So the proof of this particular expression, just like we have proved down that x and p is equals to the iota h cut, what is the proof of this? So in the next video, we are going to prove. As I have said before, the next video is purely for the mathematical things to prove the mathematics in the spin. How can we define the spin states with the help of the spinners? So these types of things we are going to study in the next video. But now this is only some of the theory things. So now let's write to the topic that there is a commutation relationship between the spin measurement, just like the position and momentum. Now, there is also some of the eigenstates and eigenvalues that are related in these things, but I know that you are not familiar with these types of things. What are the eigenvalues, eigenvectors, and all that things? So I am going to discuss here. So it is very important to learn the eigenvalues and the eigenvectors, because pure quantum mechanics is based upon this particular thing. What are the eigenvalues and the eigenvectors? Eigenvalues and eigenstates, let's say. Okay, eigenstates. What are these things in the quantum mechanics? Because if you have watched my previous videos in the context of quantum mechanics, I have written a very important thing. What was that? So I've written that sorry, it is also a very important relationship regarding, okay, where, okay, what I have written is that the Hamiltonian psi is equals to the E psi. Okay, you have seen in my previous video I have written this, but what exactly the meaning of this? So this is also the eigenvalue equation. This is called the eigenvalue equations, and I will explain you this particular things in the context of this famous eigenvalue equation. This is called the eigenvalue equation. Eigenvalue equation. But how? What do you mean by eigenvalue equations? What do you mean by eigenvalue, eigenfunctions, and all that things? And why so in the quantum mechanics it is necessary? So let's see with a very famous examples. So first of all, let's see the examples on understanding this. So here, suppose that I have an operator d by dx. You know that d by dx is an operator, and I operate this operator on a function e to the power x. What will happen? It is equals to the e to the power x. It is equals to the e to the power x, because you know that the differentiation of e to the power x is equals to the e to the power x. What do you mean by this particular equation? So there are some things, that is, there are some operators that apply on some functions, and it gives the function same multiply by some of the constant a, and in this equation the constant is 1, and this is called the eigenvalue equations. Again, suppose that there is another example I can take is yes, suppose that I operate, first example is this, second example is also a very great example. Let's see what happens. Suppose that I operate d by dx to the e to the power 2x. You know that with the help of the chain rule we can easily evaluate this particular differentiation. What will happen? It is equals to the 2 e to the power 2x. Again, listen very carefully. In the context of linear algebra, what happens is that when I apply some a operator, which apply some a operators to some functions, let's say f of x, to some functions f of x, what happens is that we get a here constant which is a real constant, a, let's say a which is a real, okay, a is real, and multiplied by the same function. And these types of equations are very often in the context of linear algebra in the quantum mechanics. And these types of equations are what called the eigenvalue equations. See here, I operate the d by dx, which is just similar as the a operator, to a function which is e to the power 2x. What happens is that it is equals to the 2 e to the power 2x. What happened here? This particular function and this particular function is same before and after the operation, and we get a multiplied by a some particular constant 2, and which is what here a I have tried to explain, which is what here a, and d by dx is what here the operator, and ex is the function. So that's the meaning of the eigenvalue equation.
eigenvalue equation. This is the meaning that in some examples there is also various types of example in which you apply some a operator to a function. What happens is that you get some constant multiplied by it, and you get the function same as it is that was before the operation, as you can see that in this example. And in this example also, you apply the d by dx to the e to the power x. What you will get? You get e to the power x again, same, multiplying by a particular constant a, which is equal to the 1. So this is the called the eigenvalue equation. But what is eigenvalues and eigenstates? So this particular a operator, and this is f of x. So this f of x is what called the eigenstates. So this particular f of x is called the eigenstates, and a is called the a is what called the eigenvalue. What? Eigenvalue. And these are called the eigenstates or eigenfunctions. Basically they are the same. Eigenfunctions and eigenstates are same. Let me write because you got confused. Okay, so eigenstates is as similar as eigenfunction, is same as eigenfunction. So please do not confuse between this. These two things are equal. Eigenfunction. Okay, and this is called the 2 here. 2 is called the eigenvalue. The constant that is we obtained after applying the operator is what called the eigenvalue, and this whole equation is called the eigenvalue equation. And this what happens in the quantum mechanics. When I apply the Hamiltonian operator to the wave function, what I get is that a constant e, and the wave function same as it is, and that's why we call this an eigenvalue equation. And what we found is that this particular a constant here is the energy. Here a is the energy, and this is the usefulness of the eigenvalue equation. Like in the infinite square well, we derive the energy of a particle in an infinite square well, which is a quite difficult method. But using this method, what you have to do is that you have to just apply the Hamiltonian operator. Here it is a Hamiltonian operator to the wave function. You will get a constant multiplied by it and multiply by the wave function it is. And the constant that you get is what called the energy, and this is the usefulness of the eigenvalue equations. So this is the basic meaning of the eigenvalue equation. So in the maybe in the next video, we are going in detail into the eigenvalue equations, that what are the eigenvalues of the discrete X spectrum and continuous X spectrum. But this is not the topic of this video. Maybe in the next video. I hope that you understand that what is actually the meaning of the eigenvalues and the eigenstates and eigenfunction. Both have the eigenstates and eigenfunction are same. I'm repeating it. You will get confused when you see that in some books there is an eigenstates and in some book there is an eigenfunctions. Both these two are same. Eigenfunction is what? The function. This the function in which you apply the operator. This is called the eigenfunction. So this is called the eigenvalue equation, and this is also an eigenvalue equation, and this is a very famous eigenvalue equation in the quantum mechanics. I hope that you understand it. And now let's move and to get the insight into the usefulness of the eigenvalue equation in the spin. How it is useful in the spin. Let's see here. Let's see how it is useful in the spin states. So spin states, in spin states, how is this useful? Okay, what happens is that s square s square is defined as sx square plus sy square plus sz square. It means s square spin is equals to the spin in the x square plus spin in the y axis square plus spin in the z axis square. And this is how we define the spin square. Just like you have studied in the vectors, like here in the vectors you have studied that if a is any vector quantity, if a is any vector quantity like ax, let's say ax in the x direction, a is a vector quantity, ax plus ay. If someone asks you to find out the mod or the magnitude of this particular a vector, how you will do that? You will just get root under you will just get nothing but a root under ax square plus ay square, sorry here, ax plus ay square. And this is just same as this, because if you took the root down here, it is similar as this, and that why I have defined s square as sx square plus sy square plus sz square. Okay, and this is very important thing, that this s square is an operator. Okay, so this sx, sy and sz are the operators that can give out the measurement of the spin in the x, y and z axes, remember. Okay, so these are the operators. In the next video we are going to describe that what is the guaranteed operator of this particular spin. Just like there is a momentum operator x, it is the operator that will define the momentum, in the x-axis. Just like here, sorry, so just like here, as you can see, there is also sx square, which is the momentum, which is the operator in the x direction, which measures the spin in the x direction. Okay, so when you apply this particular s square operator to the spin matrices or spin states, let's say. Okay, here is also, this is also a function. For simplicity, you will assume that this is also a function. Okay, so if you apply this particular s square to a function which is in a spin matrix, okay, maybe next video, apply to a function, what you will get is that it is equals to the h cut square. Okay, let me write out here. It is equals to the h cut square s plus 1 sm. So this is the thing. This is also an eigenvalue equation in the spin. As you can see here, let's analyze this particular expression. First of all, this s square is an operator. When these particular operators act on the spin matrices, the sm means the spin matrices, and matrices means, you know, that is often to describe a particular functions in the matrices, because it is very easy to visualize this in the matrices. That why I have written here the spin matrices, and the spin matrices are also the functions, their functions, and that's why I have written here the SMS f of x, as you can see here. So if I apply the s square to our spin matrices, it is equals to the some constant multiplied by 8 into again sm, and you know that this is again the eigenvalue equation. Just like here, f of x is f of x, here sm is also sm. Okay, and we multiplied by it h is at a square s plus 1, and this is our eigenvalue. But this is very important result that you have to remember. This result is very important. This is very important because in quantum mechanics, spin is represented by various types of matrices. Pauli matrices is used to describe the spin. Pauli matrices are used to describe the spin. So what you have to do is that in next video, I am going to tell you that this particular Sm, which I tell you to just assume a function, is a matrix which is like this x plus, but I know that you cannot understand, because in the next video I will go in detail in this particular thing. But for now, just assume that this is a function. Please don't take very much hard enough to understand it. For now, assume that this is only a function. So when you apply your s square to this particular function, you will get an eigenvalue multiplied by it into the sm. And as you can see that in eigenvalue, here are some terms that I have to introduce to you. H cut square is nothing but here's a Planck constant, reduced Planck constant. There is h cut square, h bar square. Here s is the spin quantum number. S is the spin quantum. Now you can get that how they are related, with how the spin is related to the spin quantum number and all that things. Okay, so this is the eigenvalue that you get when you apply the s square to the any of the spin matrices. In the next video, we are going to decode that the expression that I have tell you, Sm is a spin matrices. So this is the topic of the next video. I hope that you understand all the things that I have explained in that particular video, that I have explained that what exactly the spin of the particle is, but you know that the spin is something very fundamental. Just like the charge, it is a very fundamental quantity and it requires some of the deep videos to cover. Then we discuss about the commutation relationship. Just like the position and the momentum operator, the Sx operator and the Sy operator, it means the spin operator in the x-axis, spin operator in the y-axis. When you these are, you can't measure simultaneously. These particular equations means that you can't measure it simultaneously. Then we discuss about the eigenvalues and the eigenstate, that what exactly these things are. Then we discuss about the uses of the eigenvalues and eigen matrices, eigenvalues in the spin, what exactly the uses are. So I hope that you understand this. And if you have any doubt regarding this, that you want some particular videos, detailed videos on that particular topic, let me know that you want a particular topic. So thank you for watching my video.